this topic here is kind of a for all exist statement. It defines something really cool in machine learning, which is, you might say, I get a picture of 1 million cats and dogs. I get my machine to recognize cats and dogs, right? And then I give it new pictures it's never seen before. And how can I possibly expect it to know whether it's a cat or a dog, right? And we kind of define the concept using foralls and exists, but it's a little hard, right? So we could do that, or we could jump to the next topic, which is coming up with a more formal proof system. People, yeah, you want to do this? All right, so holler when you don't understand something, all right? Yeah, let's see. All right. So we're gonna state it a few times because you probably won't get it, the nuances, until we go through it a few times. All right. So the assumptions here are that the adversary doesn't give us the training data, right? Where did and neither did some God give us, kind person, fairy godmother give us the training data. The assumption is that we chose the training data randomly from the universe. All right, that's our assumption. And then we find a machine that fits the training data well, right? So in this picture here, we're imagining the training data has one real number X as input and one real number Y as output, right? So that makes each training data a point, right? It has an X value and a Y value. And why is that nice for pictures? Because then what we're doing is we're trying to fit a machine. What's the machine? The machine is the green line. And what does it do? You give it an X value, and it gives you a Y value, right? Everybody buy that? And here we're saying, hey, that looks like a pretty good machine. Does it fit the training data exactly? No, but maybe it's close enough, right? And there's this whole idea of this isn't in these slides here, but have you heard of underfitting and overfitting? Right? So underfitting, if this curve didn't match the data at all, right? Suppose your machines only did straight lines, right? Could we match this data with the straight line? Not very well, right? So that would be underfitting because the machine's not powerful enough to capture the curvature, right? On the other hand, here's my data, right? And I do this, right? Did I capture the data? Well, I went through each point, right? So I absolutely fit the training data. But you might say I overfit, right? I worked too hard to fix the training data perfectly. And the problem with that is if you take some new value I've never seen before, it doesn't give me such a good answer, right? So this answer, we might say, is better than this answer, even though it doesn't do well. It doesn't do as well, right? And why would we say this curve is better than this one? If all you know is the training data, right? With respect to the training data, there's no way this one's just not better, right? Anybody get it why this one's better? Yeah, but how do you know that? More work, perfect. This one is just too complicated of a machine, right? Well, this one's a pretty simple machine, right? And there's something, have you guys heard of axiom, somebody's Axiom's razor? It says given two theories about the world, right? This is a theory about the world, and this is a theory about the world. Which one do you prefer? You prefer the simpler one, right? So this one maybe doesn't fit the data perfectly, but it's a nice, it's not overfitting and it's not underfitting. All right. So this is where the simply memorizing comes from. All right. Here, how do I define a machine that gives you the perfect answers? Well, I write down for every input what the output is, right? I just memorize it, right? And what memorizing requires is lots of bits to be able to write down, right? So somehow we say you didn't memorize it. Somehow we want to say that, right? It's a simpler machine. Everybody buy that? All right. And now why is this a simpler machine? Well, the machine is going to be described by some weights, right? All we're going to say about the machine is that it's a big box that has knobs on it, right? And you can turn the knobs to be whatever value you want, right? So if it's a neural net, these will be the weights of the connections. But we don't care about that, right? We're just saying it's a box with knobs. And how many, and these are all real numbers, not bits, right? How many real, oh, actually, sometimes we're going to use them as real numbers, and sometimes we're going to use them as bits. All right, so in the theorem today, these are all going to be described by bits, right? You have to set bits to describe the machine, right? And the number of bits to describe the machine has to be less than the training data. All right? Why? Because maybe the output for each training data is just yes, no, right? So if I remember 1 bit per output, I'm kind of memorizing. I'm not memorizing the inputs, but I'm memorizing the outputs, right? Does that make sense? And that certainly will be overfitting. And we don't want overfitting, right? So this says you don't have enough bits in your machine to memorize 1 bit per training data, right? Everybody buy that? Then this is what we're given, right? So the oracle, right, kind of assures us, hey, you got the training data randomly. Somehow, magically, you came up with a machine that does well. And that machine wasn't described by a lot of bits. Yep. Yeah, I'm meaning it much less. In fact, we're gonna put in here a 1 over epsilon, where epsilon's some little number. Right? And now what we're going to prove is, well, maybe everything went wrong, right? You chose bad training data, something bad happened. But with very high probability, if you take a new point, a new training data item that you also chose randomly, right? The machine's going to do well on it. Right? Everybody sort of see that? And so let's go through the game, right? Right. So here, first we start off with I like to. Oh, this is just defining the game for those people who don't know it. But you guys know, the game already. I was like, this isn't on topic, but no, it's just for those people who haven't seen this before. All right. So what does the adversary do, right? In some ways, this is defining our universe. The adversary is going to define a probability distribution on training data. All right? So the universe, what does this mean if you don't know what a probability distribution is, right? So an X could be an image of a cat, and the Y could be a label which says cat. I mean, here we had it real value, but in general, right, could be something like that. And then what is our distribution? What is our universe? It's a black box machine. And what do you do with this machine? You put in a quarter and push a button. And what comes out is a random pair, right? You put in another quarter, push the button, you get another random pair. And so what is the adversary choosing, right? It kind of chooses for every possible input, for every possible XY, it gives a real number, which here's the real number P, which says, what is the probability that when I push the button, I get out this pair, XY, right? People know about randomness enough, so understand what I'm saying here, right? Like, if I have a dice, I'm going to label every side with, right? Every side with the 6. Because when you roll the die, when you push the button, you get a side of the dice with each side comes up with probability of 6, right? So here instead what we're going to do is every possible image with the label, right? There could be a picture of this pretty cat with the word cat, and it has some probability of coming up when you push the button, right? And then there's a picture of me that says cat. Well, there's some probability that that comes up. Maybe the probability is 0, or maybe there's some chance that a picture of me labeled cat comes up. Right? Everybody understand what this distribution is? Right? And the adversary gets to define this distribution. Right? It designed the universe or world of images. Right? All right, so then the adversary gets to define some other things. It has 3 parameters. Capital D is how much training data we'll have. Little m says how many bits we'll use to describe our machine, right? Epsilon will be some little teeny number about accuracy, all right? And what we need is this relationship. We need the number of bits you need to describe the machine is way, well, that's why I had the 2 arrows, right? Way less than the number of training data, right? The adversary gets to choose these things, right? And now, the adversary, we're giving the adversary so much power, all right? Remember how evil these adversaries are, right? They're out to prove you're wrong, all right? So the adversary gets to describe a set of machines, right? So it might just say our machine is a neural net where the bits, right, that these m bits, what are they doing? They're describing the machine. So maybe we use them to describe the weights on the edges, right? So the adversary gets to define the machines, and maybe it defines the machines to be horrible machines that don't do anything, right? Or maybe it defines to be really nice machines that can be smart if you train them right, right? right? So that's why it's a family machine where the weights are defined by int bits, right? Everybody buy this? So, right, when you're reading a theorem, you want to think, first logic, what did Jeff teach me, right? Who's the adversary? Who's the prover? What's coming, right? So the adversary gets to choose all of these things. We're saying for all of these things, it's going to be true. Everybody good? All right. Right? Why are we restricting this? Just a little explanation, right? We restrict the complexity of our machines because as he said, if it's too complex, we can overfit, right? We want somehow a simpler machine to describe, right? So if you had too many bits, you can write down the answers, right? But we don't have enough bits to write down the answers. Because why? Because we have D training data and we don't have D bits, right? So when we're learning our machine, we can't learn simply by writing down the answers, right? Does that make sense? Now, the proof, which we're not going to, well, we'd only give if you want me to prove it. It's surprisingly not that hard, right? The proof just is a counting thing. It says, how many machines do we have? How many, right? All right. Otherwise, we'd have overfitting. All right. Right. Somehow, what I like to think is when you learn, somehow you have to take all the information from your data, training data, and compress it. It's like, what's the best way to study? The way I used to study for an exam is I would try to summarize the entire course under 1 or 2 pieces of paper. As if, I think, suppose I could take 1 or 2 pieces of paper to the exam with me. What would I write on them, right? And the process of compressing all the information into 2 pages actually helped me learn the course, right? Right. So the compressing forces you to understand the data so that maybe you can generalize, right? Does that make sense? All right. Now, what are we going to try to prove? Well, what's the first thing we're going to grab? Right? What do we need? We need training data, right? So the first thing we're going to do is we're going to take our adversary's universe and we're going to put in D quarters and push the button, and we're going to get D randomly chosen training data, right? Does that make sense? Right, so we have our randomness is going to flip our coins. All right, and then, right, now it's going to be A implies B, right? Are we stating that there is a good machine to understand our training data? No, remember, because the adversary may have given us a horrible machine. We're proving A implies B. We're assuming, right? I don't think I have my oracle in here. Do you know why? Because I made these slides before I designed the oracle for this course, all right? So the oracle here is assuring me that I have a good machine, right? And what do I mean by a good machine? Well, we could say on most training data, it gets almost the right answer. But here we're going to talk about getting exactly the right answer, right? Going to get exactly the right answer on all but some epsilon fraction of the training data, right? Everybody buy that? So we're assuming this is the case. Now, right here, let's say it again. There's some machine in our list of machines, i.e. some setting of the weights, such that this many of the training data pairs, if you plug in the input, you get the right answer. Right? People buy that? Now, the adversary says, hey, dude, I get to design the machines, right? I could design the machines so that they don't compute anything, right? He's actually saying something worse. He's different. He's saying if there are a number of machines in the set that do the same, he gets to decide which one, right? Yeah. All right. So then what do? Right? We chose our random training data. We say the oracle assures us that there's a machine in our language, in our machines that can do well on it. Then we compute one more, we randomly choose one more training data, right? And we check our machine, how well does it do on our training data, right? Everybody get that? That's an experiment, right? We check to see whether it gives the right answer, all right? So we repeat this experiment many, many times, right? Many times we choose random data, training data, we select the machine, we grab some unknown data, we check it on our machine, right? Does that make sense? Now, anybody have any intuition here? Why should your machine is chosen so it does well in this training data, right? Why should it possibly do better on data it's never seen before? Yeah, exactly. So because the machine can't memorize the answers, somehow it's learning the distribution, right? It's learning something not just about the training data that was acquired, but it has to learn something about the universe that's generating this training data, right? And so when you get a new piece of training data from the same distribution, then it does well, right? So here, how well does it do? Well, the probability it does well is the sum of these epsilons, all right? And what do these epsilons come from? The purple epsilon is how well your machine does on your training data. And the red epsilon, right, was the gap between how big M is and how big D is. All right? So it uses those two little epsilons, right? You want them both to be small. Does that make sense? Right? That guy and that guy, right? Here, this is where the red epsilon comes from. Here's where the purple epsilon comes from. All right? Everybody good? Are you kind of following this a little bit? And you might, doesn't it seem like, still, it seems like a miraculous proof, right? How could you prove that this was always the case? Right? All right, so the adversary, for example, comes and says, come on, surely I can mess you up. Here's a piece of training data that you've never seen before, right? How are you going to ever recognize that to be a bicycle? Right? So what's our counter to our adversary? Yeah, right? Well, either it does or it doesn't, right? If it does apply, if this image has a high probability of being outputted, then with high probability, it's going to be in our training data, and we're going to know that this is a bicycle, right? And if it has a low probability of coming out, then we might not learn that it's a bicycle, but neither is it likely to come out as our extra training piece, right? Does that, everybody kind of follow that? Right? Right? The adversary got to choose the distribution on their universe, but it had to choose it at the beginning. Remember, the order in which you play the game really matters, right? If we let it give us any training data and then gave us any new data, there's no way we would be able to know what this new data was, because it would give us this picture and tell us it was a cat, right? But it has to give us the distribution at the beginning, right? Right. So the adversary can say, oh, well, I'll just make your machines really bad so they can't compute anything, right? And how do we handle this adversary who's being mean to us? Exactly, right? 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 So here, our machine is the best one from here. And if all the machines are bad, then we won't get, right? If we choose random training data and there's no machine that does well on it, right? A implies B, A is already false, then we win, right? If the adversary doesn't give us the distribution and machines that allows us to learn well, then we win this game, right? Does that make sense? Right? So that's the statement. People like that? Kind of fun, eh? How brave are you? You want to see the proof? Yeah, people want to see the proof? Let's see if I can find it. They're not in the slides, but it's, yeah, it's such, I find it's, in some ways, it's the proof that you need to know in this world right now, right? Machine learning is about to take over. You know, you're going to lose your job. You're going to lose, you know, how does it work? And it's partly this theorem that allows us to do it. So we're just going to go over here to machine learning. And then we're going to do generalizing. Oh, all right. So all right, what are we starting with here? All right, so this is just the game in which we have a bag of coins, and each coin comes up heads with some probability, right? And we're trying to learn which coin is which. In fact, given a coin, we want to calculate what probabilities does it come up heads, right? Right? So how can I learn, given a coin, how can I learn the epsilon, right? So what you do is you flip it a few times, right? And so all right, so here I flip it lots of times, and the purple epsilon is the fraction that comes up bad. You know, the coin has a bad and a good on it, right? And when I flip it 1,000,000 times, and epsilon purple is the fraction of times it comes up bad, right? And the blue one is the actual probability of it coming up heads, right? Everybody get this? And we just measure how close we are, right? Does that make sense? So what the law of large numbers tells us, the more time we flip the coin, right, the more accurate our purple number will be, and the closer we will be to the actual number, right? Everybody buy that? All right, so Chernoff bounds help you bound this, and I was going to say I grew up knowing Chernoff bounds, but at some point I learned Chernoff bounds. But when I was studying this topic, I learned a slightly different version by some other guy. Anyway, what does it say, right? If you flip a coin that has the blue distribution, and you flip it 20 times, right? And then right? Then the expected number of heads is going to be, right? This times this is going to be 5. Everybody buy that? So here, what do we got in this picture here is you repeat the experiment many, many times. And if 5 comes up, you put a little box here, right? And if 9 of them come up heads, then you put a guy here, right? And this says that you're most likely to get 5, right? And the further away, you might get, you flip the coin 20 times, right? You might get 15 heads, right? But it's not very likely. Everybody buy that? Everybody got this idea? This distribution, right? It's called the binomial. It's binomial because it's a discrete number of times. If I flipped it an infinite number of times, then it would turn into what distribution? A normal distribution, right? So the normal distribution is a little smoother. Like, for example, if I flip it 20 times, it's not going to come up 21 heads, right? But a normal distribution goes out to infinity. All right, so here's the theorem that this guy came up with, right? He says the probability, right? Here's the number of heads that we came up with, right? The probability that the number of heads that we came up with differs from the expected number. The probability that we're off by some small amount. Here's the expected number, right? Epsilon d, blue epsilon d, is the expected number of heads, right? What's the probability that epsilon fraction of the expected is what we're off by, right? We're off by epsilon of the expected, right? And it becomes exponentially small, right? So this actually is the Chernoff bounds. This is the one I learned. But the problem with Chernoff bounds is that we don't know the blue epsilon, right? So so instead, we come up with the new method where we say this is the expected fraction of heads. This is the fraction that we obtained. And we want to simply ask what's the probability that we deviate by some red amount, right? And we say that probability is really small, right? Here, D is our training data, right? We have lots and lots of training data. And so epsilon squared D, right? That's going to still be a big number. In fact, anybody remember epsilon D, where it comes from in our proof? That was M. Remember, M is the number of bits we had to describe our machine, right? So we still need this to be big. It's the number of bits describing our machine. It's big. So this is exponentially small in that. Are people good? Are you still wanting to do this? This is all right. So here's Jess. If you want more on probability theory, I have a whole page. Any questions? Right? What do you have to remember from this? It's just completely intuitive, right? You have a coin that it comes up heads with the blue probability, right? You flip the coin some number of times. Oh, you can flip the coin capital D times. Yeah? And you get purple number of heads, right? What's the probability? And then you have some epsilon that you want to be within, right? If you set D, here you have some epsilon you want to be within. You set D to be bigger and bigger and bigger. This probability is going to get smaller and smaller and smaller, right? So that the probability is really, really small that I deviate by this red amount, right? The epsilon is how different do you allow, right? So suppose you're a company and you have this coin and you know it has some blue epsilon that you want to learn, right? So you want to think two things. You want to think, how close? I'm never going to get epsilon perfect, right? How close do I want to be? What's my tolerance of error? And I'm going to come up with some red, right? I want to know within this red, right? Everybody get that? And you can choose whatever red you want, right? And then you want to define how much risk you want, right? You might always be wrong. You make D, you flip the coin a billion times, you still might be wrong, right? But what's the probability of error that I'm willing to, the probability of a bad event? How averse am I to tragedy, right? And you set this probability to be as small as you want, right? Now, given the red and given the blue, right? Given the red and given the D, I don't know the blue, right? The company can say, I want my red to be really, really small. I want my probability to be really small. So this equation will tell you how big D needs to be, right? And then this says, if you flip the coin that D many times, then you're going to get within the accuracy you want, within the probability that you want, right? Does that make sense? Very useful for doing things in the world, right? Right? And I read these things that sometimes say the people who are designing cars they want to calculate, well, what's the probability people die? And how much it's going to cost us when somebody dies, right? Because they're going to sue us. And how much is it going to cost us to make sure people don't die? And they do the math, right? And you could say that's bad because if they spent more, then fewer people would die. But on the other hand, if they spent more, you couldn't buy the car, right? There needs to be some trade-off, right? I mean, how much are you willing to spend so that nobody dies of some disease? Are you willing to spend $1 million per person? No, we don't have $1 million per person, right? How much is OHIP willing to spend to keep you alive? These are the games. Everybody get that? That's how insurance works. That's how OHIP works. OHIP has to decide whether to cover you. They say, well, if I spend this much, then there's this probability I'll keep you alive. Is it worth it to us? Right? All right. Here's just saying it again. Right? My estimate is of this value is off by more than epsilon for my current coin. It has small probability. Right? All right. Now, here's another thing is I don't have that many coins in my bag, right? And I want to know the right answer. Are we running out of time?